This video is purely over the structure of interstitial and substitutional alloys. For a comprehensive lecture of the structure of metallic bonds and metals, please refer to the video I have over this on my channel. Because alloys are one of the easier topics in chemistry, and I try to make my videos as entertaining as possible, today's video is going to start off with a little bit of a history lesson. If you're super duper on a time crunch before your test and you can't spare a minute, skip to the timestamp I've left in the video description to get to the lesson. For everyone else who's sticking around, stay with me. For about the first 2.5 million years of our Homo genus existing, we used stone tools. Stone tools are great for a couple of reasons. I mean, you can literally find rocks anywhere. You can even make them sharp if you find the right type. But they also have a few major downsides. They break easily. You have to constantly take care of them. And they're not even shiny. Around 6000 BC, in the Indus River Valley, whose map I've pictured here, humans began smelting copper, the first instance of us using metal. Copper is quite strong, being able to withstand a yield force up to 220 megapascals, or 220 million base units of pressure. However, one day, by complete accident, something revolutionary happened. The correct combination of rocks containing copper ore and a mysterious metal were used to make a campfire. When they combined, they formed the first alloy known to mankind, tin bronze. Copper was great, but bronze, that was a whole nother deal. It could max a yield force out at 450 megapascals. A quick side note I want to add here, the exact values for strength depend on conditions, but the important idea, and the reason I'm including these values, is to signify that alloys are stronger than their base metals. Back to the topic at hand. We even named a whole age of history after bronze, and then we named a collapse after it. Since then, humans have continued to perfect their recipes for even better combinations of metal to create alloys. Steel, brass, aluminum alloys, the list goes on. In this video, we will explore the two categories that alloys fall under and why they are stronger than their base metals. Let's begin. The first category that alloys can fall under is substitutional. Substitutional alloys are alloys that contain two or more metallic elements of a similar size. For instance, bronze, which contains copper and tin. Drawing the particulate model for bronze below, you'll see the copper atoms in red and the tin atoms in gray. Another thing you should notice is the difference in size between these two atoms. Copper atoms have a diameter of 128 picometers, whereas tin atoms have a diameter of 140 picometers. Because of this, when we combine these two elements with one another, some tin atoms will replace copper atoms, and an alloy will form. In this case, it's bronze. It's important to note that, in pure copper, the atoms would be arranged in near-perfect rows, as I've drawn here. Because of this, they can easily slide past one another if a force were to be applied correctly. In bronze, however, the larger size of the tin atoms results in a more awkward structure, in which the copper and tin atoms are not perfectly aligned with one another. Because remember, the tin atoms are bigger than the copper atoms. This means that if a force were to be applied, it would be a lot harder for the atoms to slide past one another, as there would be much more resistance between the atoms. This is why bronze is stronger than just pure copper. You need to understand this. Alloys are stronger than their base metals because differences in sizes of the atoms allow for less slippage. You need to know that. This is also why alloys commonly have slightly less conductivity than their pure metals. The awkwardness of the structure reduces this property. We see a similar phenomenon occurring in interstitial alloys. Interstitial alloys are alloys consisting of a metallic element and another metallic element which is much smaller. For instance, steel, which I've drawn here. Steel is made up of iron, represented by the gray circles, and carbon, which is represented by the much smaller black circles. The diameter of an iron atom is 126 picometers, whereas for carbon, this value is only 70 picometers. Because of this, the carbon atoms can easily fit in between the spaces left by the iron atoms. This greatly increases the strength of the substance. On its own, iron has a yield strength of around 50 megapascals, whereas for steel, this value can exceed 690 megapascals. Again, you need to understand that this is because the carbon atoms are preventing slippage within the alloy. If a force were to be applied to this alloy, the small carbon atoms within the iron atoms are going to provide more resistance and prevent against slippage far greater than if this was just pure iron. This is something I want you to drill into your head. Alloys work because they prevent slippage. Something you may also have noticed by now, but that I just want to clarify, generally, interstitial alloys will be much stronger than substitutional alloys, as the effectiveness of tiny gap-filling atoms is nearly unstoppable. If you'll remember back to the substitutional alloy I drew, only some of the copper atoms were replaced by tin atoms, whereas here, every single iron atom is touching another carbon atom. So again, interstitial alloys are going to be stronger than substitutional alloys. Just to finish this video off with a little recap, remember, substitutional alloys are when similar sized atoms replace each other. Interstitial alloys are when much smaller atoms fit in between larger ones. Alloys work because they disrupt the 3D lattice and reduce slippage. And also keep in mind that because of this disruption, alloys generally have less conductivity than their base metals. And congratulations! That's all you need to know about interstitial and substitutional alloys. Pretty easy, right? If you feel lost or confused, check out my other, more comprehensive video on metallic bonds, or try rewatching parts of this video. If you're still not getting it, take a break and come back later. Thank you for learning about ancient Mesopotamian valley citizens with me, and thank you so much for watching.